where we left off. So this is where we are. And so we have our protein, we have the spheres telling the docking program where we want to dock. Now we need to generate what's called a scoring grid. So what this is going to do is it's going to go in this area, and it is going to figure out what all the electrostatic forces that exist at every single little point in space around here. So that when we put our small molecule into that, we can do calculations to figure out how the two are going to interact with each other. So we need to make that scoring grid. The first step is to make what we call a box. The box is simply going to define where on this protein we want to generate our scoring grid. Now, we're going to have to decide how large we want our box to be. What it's going to do is going to ask us how far away from our spheres do we want to go. The bigger the box, the more likely you are to get a molecule that docks someplace that you don't want it to. Also, the bigger the box, the more computing time it's going to take to do the docking. However, if you make the box too small, you're going to really limit in what orientation your molecule can dock. So you can get something that's not the best binding pose. And so you think the molecule is going to bind one way, but in the real world, when you add the molecule to the protein, it can bind however it wants. And so you may not get appropriate docking. And so we have figured out that 4 angstroms buffer in each direction around the spheres is a good number, at least to start with. Sometimes you run into errors, you need to change that. So we're going to make our box in our SIGWIN here. And we have a program called showBox. So here it's asking me the dimensions, and so I'm going to say 4 angstroms in each dimension. And it's 4 angstroms in each dimension away from my sphere selected .sph file. And I'm going to name this 4box.pdb. It's my box, so I'm going to put box in the file name, and the 4 tells me that I told it a dimension or buffer of 4 angstroms. Sometimes if I do the docking with 4 and I decide I need to go bigger, I'll make a second box. I'll name it something like 6 box or 8 box or 5 box or 2 box. That way I can keep track of what file I'm using during each docking and keep track of which file is which. So that is a very quick process. So now we can it's a PDB file, so we can open it in Pymol. So here it is. So here are the old version of Pymol didn't put these spheres here. I don't like that. Can I hide spheres? Yeah, there we go. So here you can see the box. It completely encloses our binding pocket. So we're going to make a very, very dense scoring grid inside of this box. And our molecules are not going to be allowed to leave this box. So I need to make the grid. And in order to do that, we need to have what we call a grid.in file. So if you download the manual, or if you go to the website, actually it's not in the manual, if you go to the website for the docking program, they have a file that you can download. It's a template, which I always just copy it from a previous docking experiment. This is again, is just a text file, and this is the commands, the instructions, the parameters that we want the program to use. I always just use the defaults. However, some things we need to change, like file name for our specific docking experiment. And so I am still using elmo.mol2, so I don't have to change that. But our box file is 4box. I'm going to change that to 4box.pdb. This sometimes you need to change. This is a definition file. This is what it uses for its calculation. And this is part of the program, but you need to make sure the program knows where to find it. So this is just a Linux file location telling it to go up a folder, into the parameters folder, and find it there. So we're doing our docking in this bin folder. If I go up 1, I have to go into parameters, and here is the file that I'm telling it to use. So that's simply what I need to do. So I change that from the default when I downloaded so that it could actually find the file. If you didn't change that, it would give you an error telling you it couldn't find it. So then you have to come in and change where the file location is. I also changed this. This is going to tell it what file name I want the output to be. When I make the grid, it's going to make either 2 or 3 files, and I'm going to call it grid. But actually what I'm going to do is I'm going to change this to 4box. Okay? This is not going to make another PDB file, so it's not going to overwrite this one. I'm going to get a set of scoring grid files named 4box that came from 4box. Because if I later on have to come back and change this to 6box, I can then make a scoring grid named 6box, and I can keep again all these files tied together. So I'm going to save that, and then I am going to run it. And so I have a program named grid, and I'm going to take the input file grid.in. And now this is where you cross your fingers and hope it doesn't give you an error. So here it didn't give me an error. It found everything it needed to do. We can see the progress of how it's going. If you had a very large grid, this time increases exponentially. And so sometimes it can take an hour or two for this to happen, but we have a fairly small grid, and so it did not take very long. If I go back into my bin folder here, now we can see there's this 4box.bump and this 4box.energy. So that is what it made. I now have everything that I need prepared to do the actual docking. And so, shoot, I did not print my instructions for the actual docking, so I'm going to have to open the file. Bear with me just a second. So these are the instructions I've been reading, and these are just notes I wrote for myself. Running. So all I need to do is I need to go doc 6, and the input is going to be lecture.in, because I'm doing this as a lecture. Now this lecture.in file I have to make. So this is in my bin folder already. I made it. I'll show you what it looks like. So these are all the parameters that go into the actual docking program. It's going to tell it how to do the docking. Now, in a lot of cases, you just leave the defaults, okay? At least to start with, but there are some things that you need to change every single time. So the first thing is what ligands we're going to use. This is the catalog that we downloaded, okay? So I'm telling it, I want to use the ligand file few.mol2. I said I saved a few in a new file, and so I just named it few.mol2. And this is in my DB folder for database. Oops, I closed my window. Oh, I did. So I have a DB folder here, and that's where my few.mol2 file is. Where? So I need to change the name of my grid files from 1box to 4box, because that's what we named it. There's another one down here. I'm going to change that from 1box to 4box. What else? Again, it's telling it where to find the parameters files. I can tell it what I want the output file to be named. I'm going to tell it to make the output file lecture. And I definitely want it to rank the ligands, so that it will give me a file with the best ones first and the worst ones last. That makes it much easier to deal with. Now, there's a lot of parameters that we can change for the docking. Okay, I'm not going to go through a lot of them, but I'm going to point out a few of them for you. So number one, I want to point out the minimize ligand. So this is energy minimization. Remember from chemistry that molecules want to exist in the state with the lowest energy. So what we're essentially telling the program is the three-dimensional structure of the molecule we gave you isn't necessarily already energy minimized. So before you dock it, minimize it. Okay. You can also do flexible growth. So flexible means, is the molecule able to have rotatable bonds while you're doing the docking? And generally you want that to be yes. By putting yes, you're going to increase the computing time needed. And so sometimes if I'm docking literally millions of molecules, the first dock run that I do will have a rigid molecule to find the ones that are the best guesses, and redock maybe the best 1,000 that are with flexible ligands. Okay, so that is that. So I'm going to save this because I made changes. So this is now my lecture.in. I'm going to come back and I'm just going to run this. And again, I'm going to cross my fingers. I hope I don't get an error. And of course I did. This is because I added. This is the first time doing docking on this particular computer, and so there's some things I haven't put into. There we go. So it is thinking. The docking will take a little while. We'll watch it happen. I won't sit here and make you watch the whole thing. But in general, with these particular parameters, it should take about a minute per molecule. And I think there's about 10 of them that I'm docking. So we'll wait till the first one comes up, and then I'll pause it, and then I'll restart once everything is finished. So it is right now taking the molecule one at a time and rotating it around and trying different orientations in our box that we made and trying to overlap as many of those spheres as possible. And so it's going to give a score for every single thing that it tries. It's going to take the best one for each molecule and give that to us. So when it finishes one molecule, our command line here is going to shift down a little bit. It's going to show us the name of a molecule and the scores that it received. So hopefully this does not take all that long because I'm already out of filler things to tell you. Come on. Did I not talk for a minute? So there we go. So here, the first molecule it did, this was the name. Second one was very quick. So this is the name of the molecule. And so it took 83 seconds. And it's telling me some parameters. It said it tried about 6,700 different orientations. So that is how it's shaped in the pocket. It tried 2 different conformations, and it gave me these scores. So what do these scores mean? The grid score is simply the sum of the van der Waals score and the electrostatic score. The internal energy is not included in the grid score, but you can look at it to kind of get an idea of whether it was good or bad. So remember, things happen in physics when energy changes are negative. So a grid score that is positive is going to be very bad. So this is not going to happen. Let's tell you this is a bad molecule. If we look at the individual scores, the van der Waals scores are the interaction between molecules and the change in van der Waals forces. The ES are electrostatic forces. So we see here that it had a negative score for electrostatic, but it wasn't nearly strong enough to overcome the very, very bad van der Waals forces here. So our overall grid score is 57. This one has a negative overall grid score, so it is going to be better. Here, this one is even better. So it's going to go through the whole thing, do each one. I'm going to now pause this, wait for it to finish completely, and then restart the recording. Okay, so it finished. And you can see that there were 6 of them here. It took 355 seconds to finish. So let's look at what it gave us. Lecture rate. So this is the output file. It's a mol2 file. And so what we're looking at are the 3-dimensional coordinates of the best pose for each of our molecules. And they're ranked. This was the best one with a grid score of -30. The next one was -24. So what we need to do, if we want to look at these, is we need to separate these out into individual files. We can't open this, even though it's mol2, and PyMol can open a mol2 file, we can't open a file that contains multiple molecules. It turns into a big mess on the screen. So what I'm going to do is I am simply going to copy the first molecule out of here into a new file, and then save as. I'm going to name this, let's just say top.mol2. Looks like I already had the same idea another time. Top.mol2. Now, if I go back to PyMol, I should be able to open that. This. I need to hide our spheres. We can leave the box. So there is our molecule, and it is docked within our box, mostly in our window. It's somewhat in the window. And so we have a couple of options if we wanted to make this better. We could either go through and look at the other ones, maybe the next one down is more in our window, or what we could do is we could come, we likely had a sphere that was right here kind of on the border. We might be able to delete that sphere, redo the docking, and get this to shift over a little bit further. But that is the end. We have taken a protein that we downloaded from the internet, taken structures of small molecules that we downloaded from the internet, told the program where we wanted to dock to, prepared everything, had the docking done, and learned that this molecule is predicted to be the best binding of the ones that it docked. And so we could potentially order this molecule or make it ourselves and try it and see if it has the desired effects that we want. So I hope this was helpful to you. I hope you didn't sit here for probably 45 minutes at this point and you got nothing out of it. Again, I don't expect you to be able to do this. I'm not going to ask you questions about what were the commands that I used for this, what was the program I used for that type of thing. I'm going to ask you general questions. Okay. I really enjoyed doing this. If you haven't figured that out yet, I'd be happy to answer any questions that you